Students, welcome to our today's presentations. We are going to look at a thorough revision on physics paper 1, a paper that was done in the year 2017. We are going to see how we handle physics questions, and remember to subscribe to our YouTube channel, and also like and share and comment. Remember, your participation is so much important as much as our presentation is concerned. So we are going to start right away with the first question, and the first question in section A reads: in order to determine the size of an oil molecule, a student performed an experiment using 5 oil drops to make a circular patch of the oil on the surface of water in a water bath. State 2 assumptions made by the student during the calculations. So remember, this is an oil drop experiment, and in this experiment the student aimed to determine the size of the oil molecules by observing the behavior of the 5 oil drops on the surface of water in a water bath. The methodology involved creating a circular patch from the oil drops, and certain assumptions were made during the calculation to analyze the size of the molecule. So the first assumption made is that the oil drop is spherical. The second one is that the oil patch was circular, and the third one is that the molecular diameter is uniform. So these are the assumptions that the student had to make in order to make calculations more uniform. The second question reads: in an experiment to determine the density of liquid R, a student obtained the following data. The mass of the empty density bottle was 55 grams. The mass of the density bottle plus the mass of water was 80 grams. The mass of the density bottle and the mass of liquid R was 70 grams. So this is an experiment that involves determining the density of substances using the density bottle. So from this data we can find the mass of water to be 80 grams minus 55 grams, which is 25 grams. That is the mass of water. The mass of liquid R is 70 grams minus 55 grams, which is 15 grams, and we are given the density of water to be 1,000. This one, 1,000 kilograms per cubic meter. Now our first result will be 25 grams as the mass of water, 15 grams as the mass of liquid R. The density of water, we can convert it to grams per cubic centimeter. This is because the data we are given is in form of grams, so we change everything to the SI units. The volume of water can be calculated as the mass divided by the density, so which is found to be 25 cubic centimeters. Also remember that the volume that water occupies in a density bottle will be the same volume that the liquid R will occupy in the same density bottle. This means that the volume of liquid R is 25 cubic centimeters, and its density is calculated by mass divided by volume, which is 15 grams divided by 25 cubic centimeters, and is found to be 0.6 grams per cubic centimeters, or we can multiply by 1,000 to get 600 kilograms per cubic meter. The third question reads: it is observed that when 20 cubic centimeters of alcohol is mixed with 20 cubic centimeters of water, the volume of the mixture is 39 cubic centimeters. State a reason why the volume of the mixture is not found to be 40 cubic centimeters. So when alcohol and water are mixed, the molecules of each substance occupies space, causing the total volume to be less than the sum of individual volumes. This comes from particulate nature of matter, where we know that water has intermolecular spaces, and when it is mixed with alcohol, some particles of alcohol occupy those intermolecular spaces, making the total volume to be less than 40. The intermolecular spaces are not fully filled, leading to a volume less than the simple addition of alcohol and water volume. So the simple answer for this question is that the spaces inside the water molecules are occupied by the alcohol molecules. The fourth question reads: When a liquid is heated in a glass flask, it is observed that the level at first goes down and then rises. Explain this observation. So we have a glass flask and some liquid inside. So when this flask is heated, the glass flask expands upon heating, initially causing a temporal decrease in liquid level. The glass expands first before the liquid. This means that the liquid must drop first, but after some time the liquid catches heat and also it expands. The rate of expansion of the liquid is more than that of the flask. This means that the liquid expands more, then that is why the level rises again. So subsequently the liquid expands as its temperature rises further, resulting in an overall rise in the level. So the simple answer to this question is that the flask expands first before the liquid, then the liquid expands more. The next question, that is question 5, reads, Figure 1 shows a uniform golden bar at equilibrium with two cans Y and Z of equal masses but different diameters. These cans are here, you can see them. The can Y has a shorter diameter than can Z. So this comes from turning effect of force, where we're seeing we have the moments, we have this one causes an anti-clockwise moment and this one causes a clockwise moment, and for it to be equilibrium, the weights of these cans must be equal. So the cans are simultaneously filled with equal volumes of water. This means that the volume will add the same weight, meaning that the wooden bar remains in equilibrium. The weight remains the same on both sides. When you have added water, the water exerts the same weight on the same sides, meaning that the equilibrium, the wooden bar will remain at equilibrium. The sixth question reads, state the reason why the speed of water at the narrow section of a river is higher than at the wider section. This comes from Form 2 work, the Bernoulli effect, and here we learned as the principle of continuity, which states that the first area times the first velocity equals the second area times the second velocity. This means that there is a law of conservation that must be maintained. So if at a wider section the velocity is low, meaning for the conservation to take place at a narrow section, the velocity must be higher. So the speed of water increases at a narrow sections of the river due to the principle of continuity, where a decrease in cross-sectional area leads to an increase in water velocity. This one I've explained it. Because as the river narrows, the cross-sectional area decreases, forcing the same volume of water to flow through a smaller space, and this results in an increased velocity as dictated by the principle of continuity. Let us look at the next question. Using the definition of impulsive force, show that F is equals to M. Using the definition of impulsive force, show that force is equals to mass multiplied by acceleration. So this one comes from Newton's laws of motion in Form 3 work. So I hope that you have studied that with your teacher. So from that law, that is the second law, we find that the impulsive force is given by change in momentum. So the impulse is the force over a period of time. So it is force times time is given by change in momentum, and the change in momentum is the final momentum you subtract initial momentum. The final momentum is given by the mass times velocity v, but this velocity is v represents the final velocity, minus the same mass times the initial velocity, which is given by u, so which is this one. So the impulse is given by mass times final velocity minus mass times initial velocity. If we rearrange this equation, we get force is equals to mass times final velocity minus mass times initial velocity, you divide by time. Because mass is the same, you put it outside, we get the force will be equal to mass into final velocity minus initial velocity divided by time. So in linear motion from 3 work, we learned that the acceleration is given by the change in velocity, which is final velocity minus initial velocity, you divide by time. So if we look at this one, it is the change of velocity divided by time, and that is acceleration. So acceleration is final velocity minus initial velocity divided by time. So we have all of this as acceleration. Therefore, we find our equation as force is equals to mass times acceleration. So make sure you have a good background knowledge of Newton's first law, especially the second law of motion, for you to be able to understand how to derive this equation. Question 9 reads, Figure 2. Question 9 reads, Figure 2 shows a round bottomed flask fitted with a long capillary tube containing a drop of colored water. So the diagram below, you can see there is a round bottomed flask, and in most experiments, a round bottomed flask is used to allow, because it enables uniform circulation of heat or temperature. And there is a capillary tube, and there is a drop of colored water. A drop of colored water in this experiment is used for feasibility purposes. So the flask is immersed in ice, and for some time. The flask is immersed in ice for some time. So you are supposed to state the observation made. So in this case, the drop rises first, then falls. When a round bottomed flask is immersed in ice, the air inside the flask contracts, creating a partial vacuum. So the contraction of air in this flask creates a partial vacuum. This causes the colored water in the capillary tube to rise initially. So initially, when the vacuum is created, a partial vacuum is created, the drop rises fast, but then falls as the temperature equilibrium is established. So let us look at question 10. State one assumption for the experiment carried out to verify gas laws. So you have done gas laws in form 3, the end of physics, and in chemistry, the beginning of the syllabus. So in those topics, we looked at the major laws of gas law, that is Boyle's law, Charles' law, combined gas law, among others. So there are some assumptions made, and the main assumption made while conducting experiments involving gas law is that the gas is ideal. I want to give a simple explanation. An ideal gas is an imaginary substance with particles that have negligible volume and no intermolecular forces. So in these experiments, the researchers assume that the gases have negligible volume and they don't have intermolecular forces. So this simplifying assumption allows for mathematical relationship in gas laws, making calculations and predictions more straightforward, particularly under certain conditions. So if we could have catered for the negligible volumes and the intermolecular forces in those gases, the calculations could be much complex. That's why the scientists assumed that the gas is ideal when making calculations. So thank you for following up this presentation, and I hope that you have learned something. And also I'm going to share a video shortly about section B. So section B of physics is very important because it contains so many marks. So make sure to subscribe, like, and comment, and also share with your peers so that this video will reach a much far audience. Thank you.